In this video, we'll define stopping times and state the Martingale Stopping Theorem. To motivate the Martingale Stopping Theorem, let's begin with an observation. Suppose that z0, z1, ... is a martingale with respect to x0, x1, ... Then I claim that for any t, the expectation of z sub t is equal to the expectation of z0. To see why, let's just do it for z1. We have that the expectation of z1 is equal to the expectation of z1 conditioned on x0. That's because this outer expectation will kind of integrate away this x0. But by the definition of a martingale, this here is just z0. So this is the expectation of z0. So that shows that the expected value of z1 is equal to the expected value of z0. And you can see that if you were to repeat this, you would get this for any t. Let's see an example, or perhaps a non-example, of this phenomenon. Suppose that x0, x1, ... are independent fair coin flips, so heads or tails. If xt ends up heads, then you gain $1 at time t. And otherwise, if xt is tails, you're going to lose $1 at time t. And let's let zt be the amount of money you have at time t, starting with z0 equal to 0. So zt is just a random walk, +1 or -1 independently at each step. We just argued that the expected value of zt is equal to the expected value of z0 for any t. Let's try it for some particular t's. In particular, let's try it for t, capital T, which is a random variable that is the first time little t, so that the absolute value of z sub t is equal to 10. If we work this out, we see that the expected value of z sub capital T, well, with probability 1/2, it's going to be +10. With probability 1/2, it's going to be -10, because there's no preference for which side that this happens on. So this is going to be 1/2 times 10 plus 1/2 times -10, which is equal to 0, which is indeed the expected value of z0, since z0 is always 0. Okay, so that worked out. But how about this next example? T prime is going to be the first time t, so that z sub t is equal to 10. Then we have the expected value of z sub t prime is equal to, 10. Because by definition, z sub t prime is always going to be equal to 10. In particular, this is not equal to the expected value of z0, which is 0. So what's going on here? This does not seem to conform with this statement that we just proved. If it's not clear to you what's wrong with this, pause the video now and figure it out. Okay, so the issue is that t and t prime are random variables. We only proved the statement that the expectation of zt was equal to the expectation of z0 for some fixed little t. It doesn't work if capital T is a random variable, because then this expectation, does funny stuff to it. So it's not automatically true that the expectation of z sub capital T, this random variable, is equal to e sub z0. So in some sense, with our first example, capital T, we just kind of got lucky that this happened to hold. And with t prime, it didn't hold. But this example does raise a question. Here, what is the difference between t and t prime? That is, for what random variables, capital T, does this hold, and for what random variables, capital T prime, does it not hold? We're going to answer this question with the Martingale Stopping Theorem. But first, we'll need some definitions. Let's define a stopping time. So here's a definition. Given a discrete time process, x sub t, for example, x sub t could be a Markov chain, a martingale, or anything else, an integer-valued random variable t is called a stopping time for the sequence x sub t if the event that t is equal to I is mutually independent of all the events xj conditioned on x naught up to xi for all j greater than I. Informally, this says that whether or not t is equal to I depends only on x naught, x1, dot 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 up to xi. It doesn't depend on any of the stuff that comes after. So this is kind of why t is called a stopping time. It's like a rule for when you stop your walk, and you need to be able to know at the time that you should stop. You don't have to look into the future to figure out whether or not you should stop. To illustrate this definition, let's see some examples or some non-examples. So let's say we're in the same situation as before. The xi's are independent fair coin flips. You gain $1 for heads, you lose $1 for tails. zt is the amount of money you have at time t, and you start at z naught equals 0. Question for you: which of these random variables are stopping times? Pause the video now and think about it. Okay, so the answer is that these two are stopping times, and this one is not. Intuitively, that's because t1 and t2 we can figure out based only on what's happened so far. We only need to know the history at time t to know whether or not we've reached 10 or plus or minus 10. On the other hand, to figure out whether or not we've reached t3, we have to look into the future. We need to know whether or not we've seen 10 for the last time, which we can only know if we kind of look ahead and see what's going to come next. So once again, a stopping time is kind of like a rule telling you when to stop that you can actually act on. So stop as soon as you see 10 is a reasonable thing to say, but stop when you see 10 and you're never going to see it again is a little bit less reasonable. You don't actually know if that's occurred without looking into the future. With these definitions, we can now answer that question that we had before. That is, when does the expected value of z sub t for some capital T, some random variable t, equal the expected value of z naught? And the answer to this question will be given by the Martingale Stopping Theorem. So it says the following. Suppose that zt is a martingale with respect to xt, and let capital T be any stopping time for the xt's. Whoops, there's a typo here. These should be zt's. Let me fix that. Okay, typo fixed. The conclusion says that the expected value of z sub capital T is equal to the expected value of z naught if any of the following three things hold. First, if there exists some constant c, so that for all I, the absolute value of zi is strictly less than c. Second, if there exists some constant c, so that with probability 1, t, my stopping time, is strictly less than c. Or thing 3, there exists some constant c, so that for all I, this martingale difference, zi plus 1 minus zi, conditioned on everything before, in expectation is strictly less than c, and the additional constraint that the expected value of t is finite. So this theorem gives three different sufficient conditions for when this holds. It's worth noting that none of these conditions are necessary. Okay, so we're not going to prove this theorem in this class. It's a little bit beyond the scope of what we've done here, although you might see a proof if you take a measure theory class or something like that. However, we are going to use it. To see this theorem in action, let's return to our original example. I've copied it up here. We've got the xi's are independent coin flips, and the zi's are the amount of money you have at time I. Heads, you gain $1, tails, you lose $1. You start with $0. Okay, so our first example was capital T, which we now recognize as a stopping time, was the first time t, so that the absolute value of zt was equal to 10. So capital T is the first time that you either hit plus 10 or minus 10. Can we apply the Martingale Stopping Theorem to this? I've copied the Martingale Stopping Theorem down here. Why don't you think about it now and pause the video for a second? Okay, so we can't quite apply the Martingale Stopping Theorem to the zt's directly, but we can apply it to a very similar thing. And in particular, we can apply thing 1. So what we're going to do is let z twiddle sub t be equal to z sub t, if we haven't stopped yet, if t is less than or equal to capital T. And we'll set it equal to z sub capital T if little t is greater than capital T. So that is, we're basically just going to run zt until we hit this stopping time, and then we're going to stop. We're just going to fix it at whatever that was. And we'll call that the z-twiddles. Now, as far as the expected value of z sub capital T is concerned, we have the expected value of z sub capital T is equal to the expected value of z twiddle capital T, because they do exactly the same thing until they hit t. And we can actually apply the Martingale Stopping Theorem to this z twiddle of t. The first bullet point holds. Because for all I, zi is going to be less than or equal to 10, so we can take c equal to 11 or something like that, and this point will hold. So now the Martingale Stopping Theorem says that this is equal to e of z0. And that's exactly what we observed before. On the other hand, let's consider this random variable t prime, where we saw that this did not hold, that the expected value of z sub t prime was not equal to the expected value of z naught. So it better be the case that none of these things, 1, 2, or 3, are going to apply to t prime. So why don't you pause the video now and think about that. Okay, so indeed none of 1, 2, or 3 apply to t prime. And intuitively, the reason that they don't, for all 3 of them, is that z sub t, this random walk, might wander off to minus infinity without ever hitting positive 10. So in some sense, this answers the question that we had at the beginning of the video. What's the difference between capital T and capital T prime? So that capital T has this nice behavior and T prime does not? Well, it's because capital T satisfies one of the conditions of the Martingale Stopping Theorem, or at least something very similar to it does, but capital T prime does not. Okay, to recap what we saw in this video, a stopping time for x sub t is a random variable capital T, so that you can tell if time capital T has occurred based only on what's happened so far. You don't have to look into the future. The Martingale Stopping Theorem gives sufficient conditions for when the expected value of x naught is equal to the expected value of x sub capital T. You might be wondering at this point, okay, I guess that answers this artificial question that we came up with at the beginning of the video, but why should I care whether or not this holds? In the next video, we will see a couple of examples of why we should care. In particular, we'll be able to use the Martingale Stopping Theorem to tell us something about hitting times for random walks. So what's the first time that a random walk hits a certain value, for example. So thanks for watching this video, and see you in the next one.